All right, welcome back to Algebra 1. Today we're going to talk about simplifying radicals. Now I know in my class we've talked about radical inclusion, radical self-reliance, radical self-expression. We're going to use all of these when we simplify radicals. It's not quite as exciting as all of that, but anyway, a radical is basically your symbol, the square root sign. So it's the symbol, square root, like that, or this is a cube root. Or when you get into Algebra 2, you'll be doing fourth roots, you could be doing fifth roots, and all of that. So in our class, we're just going to be focusing on square roots and cube roots. And then we have this other word called the radicand. The radicand is the stuff inside the symbol. So the reason I'm telling you these is because the rules for simplifying use the words radical and radicand. So it's the stuff inside the symbol. So if I have like the square root of 2x, your radicand is 2x. If I have like the cube root of 512, the radicand is 512. So it's just the stuff inside the symbol. Now, we've worked with radicals a little bit already where we were simplifying, like the square root of 64 is 4, and if you have like 2 square root of 64, that's 2 times 8, right? Well, this little section here, if you look at all of the radicals, none of them are perfect squares. So like the first one, the square root of 3 times the square root of 5, we don't know the square root of 3 and the square root of 5. They're irrational numbers. However, what I could do to simplify this is I could just put these guys together and make that the square root of 15. And my radicand is 15 inside the radical symbol. That's a square root. Okay? B, the negative signs outside the radicals, those kind of act like negative ones, right? It's really like I want the negative square root of 2 times the negative square root of 7. Well, a negative times a negative, you know, is a positive. You can put that together to make that the square root of positive 14. And we'd have to stop there because we don't know the square root of 14. Now C is a little different. C is saying the square root of 7 times 2. Well, the square root of 7 is an irrational number. It's some sort of long decimal that goes on forever. And 2 is 2. So we can't actually put those together. However, we can write it like this. We can write 2 square root of 7, just like that. And that just means 2 times the square root of 7. Letter D, you can multiply together the radicals and you can multiply the coefficients of the radicals. So 6 times negative 2 is negative 12, and then the square root of 5 times the square root of 6 is the square root of 30. So this answer would be negative 12 square root of 30, and we'd have to stop there. If we were trying to get an estimate, you could type into your calculator negative 12 times the square root of 30 and get that decimal estimate, but that's not what we're looking for. Division works basically the same way. The square root of 10 over the negative square root of 5, that would be the negative square root of 2. Because both of the 10 and the 5 are both radicands, and they're both radicals, you just divide. Same with f. The square root of 10 divided by the square root of 5 is just going to give me the square root of 2. Now, G, we can't really do anything with that. It's negative the square root of 12 over negative 2. That we can't combine at all. You could pop the negative out on the outside and say it's the square root of 12 over 2. That's another way to look at it. It could be 1/2, negative 1/2 times the square root of 12. But basically, we can't combine the 12 and the 2 because 12 is a radical and 2 is not. But in letter H, we can. 8 over negative 2, well, that's negative 4. You just divide, 8 divided by negative 2, and the negative 12, the square root of negative 12, divided by the square root of 6 is the square root of 2. And so this becomes negative 4 square root of 2. So basically, radicals can get put together with multiplication and division, and if they're not a radical and a regular number, you would just put them side by side. Now, all radicals, there are 3 rules to simplifying radicals. They have to follow 3 conditions. Today we're only going to learn the first one, and that condition is an expression, with radicals is in simplest form when the radicand contains no factors that are perfect squares. So a radical is not in simplest form if there's a factor that's a perfect square. So you got to think through these. So take a second to look at the ones right below you and circle the ones that you think need to be simplified. So the square root of 30, think of your factors of 30. We've got 2 and 15, we have 3 and 10, we have 1 and 30. Now the square root of 1 is a perfect square, but that's not going to be one that we talk about. So the square root of 1 is kind of a special one. There are no other perfect squares that go into 30, so that one is already simplified, so we don't need to circle that one. However, the square root of 50, we're going to circle the square root of 50 because what perfect square goes into 50? Well, 2 times 25, right? 25 is a factor. Oops. 25 is a factor, and it's a perfect square. So since 25 goes into 50, that one's not fully simplified. So we would simplify it, and I'm going to teach you how to simplify that in a second. So the square root of 72. So square root of 72 is also not simplified. What perfect square goes into 72? Well, 9 goes into 72. 4 goes into 72. 36 goes into 72. So there are 3 perfect squares that actually go into 72. So that's the reason that one's not in simplest form. Square root of 35, we've got 7 and 5 and 1 and 35. None of those are perfect squares. That one's already simplified. Square root of 8, we're going to circle the square root of 8 because what perfect square goes into 8? 4. 4 is a perfect square, right? Hence the reason, one of the reasons I wanted you to memorize your perfect squares is so that you can look at a number right away and know, is it a perfect square? Is there a perfect square that goes into that number? And then the square root of 6, already simplified. So now one thing to note is that 2 of our perfect squares are 4 and 9. So if you know whether or not a number is divisible by 4 or 9 really quickly, that's going to help you. So let's review divisibility rule for 4. A number is divisible by 4 if the last 2 digits is divisible by 4. So this is going to help us with 3-digit numbers, right? Is divisible by 4. So like if I were to give you like the square root of 1024 and I said, is that in simplest form? You would say no, because 4 goes into it, and I know 4 goes into it because it ends in a 24, right? If I had the square root of 8,540, 4 goes into that number, so that has a perfect square of 4 in it. So you would know it's not in simplest form. The other good one is 9. And the divisibility rule for 9 is the sum of the digits is divisible by 9. So let's just take the square root of 72 for a second. The square root of 72, 9 goes into it. If you think about it, 7 plus 2 is 9, right? So since 7 plus 2 is equal to 9, and 9 is divisible by 9, then that means 9 goes into that number. Another example might be, I don't know, the square root of 5,049, right? That's a really big number, but you could be thinking, like, is there a perfect square that goes into it? Well, you could try 4 and 40, it ends in 49, so 4 doesn't work. But 5,049, if you add 5 plus 4 plus 9, that gives you 18. And so since 18 is divisible by 9, that means that number is divisible by 9. So just examples that will help you figure out whether or not perfect squares go into some things or not. All right, so there are 2 methods to simplifying these things that are not fully simplified. And I do want you to learn both methods because sometimes we can use the methods at the same time. But the first one is to use our perfect squares. We want to try to find a perfect square that goes into one of these numbers. So over to the left here, I've put all of your perfect squares down, right? 1, 4, 9, 16, all the way up to 12, right? There are more, but if any of these numbers besides 1, we're actually going to cross off the 1 because 1 goes into everything. And because 1 goes into everything, once you see why we do what we're doing, you're going to understand why we don't use 1. So all the other ones we're going to look at. So my advice whenever you do problems like this is to write down your first 10 or 12 perfect squares on your paper so you have the numbers to look at. So looking at 50, we want to look at our numbers here and we want to figure out, is there a perfect square that goes into 50 evenly? And we know 25 does. So what we're going to do, inside our radical symbol, which I'm going to call our jail, inside our jail, we have the square root of 50, which can be broken up into 25 times 2, correct? Now, we know that the square root of 25 is 5. So this guy, because he's perfect, can come out of jail. But he's been reformed. He's the square root of 25, which now is just the number 5. So this comes out as 5. And then inside the radical symbol is still 2. So now this is in simplest form. The answer is 5 square root of 2. Let's take a look at the next one. Negative square root of 12. Well, let's look at our perfect squares over here. It's either going to be 4 or 9, and 4 goes into 12, right? Well, we're going to break 12 up into, the negative sign just goes on the outside, the answer is just going to be negative, and we're going to break 12 up into 4 times 3. Now, our perfect squares, we find the square root of them and they come out. It's like they're in jail, because they're perfect, they get to come out of jail, but they come out of jail as a 2. The square root of 4 is 2. Since there's a negative sign out here, we're going to make this negative 2. And then inside the radical is a 3. And so negative 2 square root of 3 is actually the same thing as the negative square root of 12. It's just simplified. So we're pulling out the square roots of the perfect squares that are inside the radical symbols. All right? So now, the next one, we're going to look at our perfect square list right here. An easy one that we can automatically look at that we know goes into 480 is 4. Now, there might be a bigger one, and if you know a bigger one, you can try it. But let's just start with 4, because most of you are going to look at that and say, well, I know 4 goes into that. So we're going to break this up into the negative square root of 4 times 120. And now the square root of 4 is 2. So I'm going to pull out the square root of 4 as a 2, and that comes to the outside. So I have negative 2 square root of 120. Now, 120 is still an awfully big number. I bet that there's another perfect square that goes into it. So if I look, my next perfect square that might go into it, well, 4 would also go into it again. So let's try 4 again. So this is what we do. We have negative 2 on the outside, and inside with 120, we're going to break that up again into 4 times 30. And now the square root of 4 can come out. Now when that square root of 4 comes out, it comes out as a 2. Again, you have a 2 out here. This is all multiplication, so everything's being multiplied together. So it become negative 4 square root of 30. And then now let's look at 30. Are there perfect squares that go into 30? And there aren't. We already discovered that at the square root of 30 above. That's just 3 and 6. Neither one of those are perfect squares. 10 and 3, not a perfect square. 30 is not a perfect square. So we're done. Negative 4 square root of 30. Now, some of you may have looked at this problem immediately and said, all right, 4 goes into it pretty evenly, but like there's a bigger one, right? You could have, and now that you guys have calculators, you could just start taking this number and start dividing them by your perfect squares and see if you can find the biggest one that goes into it. Well, if you were to do 480 divided by 16, you would get 30. So another way to do this problem is you could have broken it up into the negative square root of 16 times 30. And then you could have said, oh, the square root of 16 is 4. So you pull that out as a 4, and it's negative 4 square root of 30. Same answer, one step. Okay, so if you can find the biggest perfect square that goes into a number, the problem's going to go faster. But sometimes you don't find the biggest, you just find the smallest, and then you just got to keep going until all the perfect squares are out of the number. So if you think you get this, I encourage you to stop the video and try the next 3. If you still are a little rocky, tune in. So 72, looking at our perfect squares, we're going to cross off 1, which I already did. Does 4 go into it? No. Does 9? Yeah, 9 goes into it 8 times. So I'm going to say, whoopsie, the square root of 9 times 8. Now that's mostly what most of you are going to do is 9 times 8. If you've already done the problem and you found a bigger perfect square, you're right, there is a bigger perfect square, but I'm going to go with 9 times 8 for right now. Our perfect square gets to come out of jail, but it doesn't come out of jail as a 9. It was in jail for a reason. It changed. It changed and is now coming out as a 3. So I've got a 3 on the outside, square root of 8. Now we aren't finished because what perfect square goes into 8? 4 does. So I'm going to break the 8 into the square root of 4 times 2. Now the square root of 4 can come out as a 2. It gets multiplied with the 3, which gives us 6 square root of 2. And you're done. Okay? Now, an easier way to do the problem, you didn't have to do 9. You could have gotten out your calculator, or maybe you just know 36 goes into 72, right? So if you'd gone through and divided 72 by these numbers up to 64, because 81's too big, right? You could try all of these numbers, and you would find 36 is bigger. And 36 goes into 72 twice. So another way to do this problem, the fastest way, would be to do the square root of 36 times 2. And you know the square root of 36 is 6, and what's left inside the radical is the 2, because he's not perfect, right? So only perfect squares get to come out of jail. All right, the next one, the square root of 284. Now this one's a funny one. You might have found something kind of strange about it. So if you're looking at your list, if you started with 4, you're going to find that 4 goes into 484 121 times. Now, what do you notice about the number 4 and the number 121? They're both perfect squares. So if I were to break that up into 4 times 121, both of those numbers are perfect squares, so both of those numbers get to come out of jail. So 4, the square root of 4 is 2, the square root of 121 is 11, and you have nobody left in jail. Everybody got to come out, and you have 2 times 11, which is 22. So what that means is that the square root of 484 is 22. 484 was already a perfect square, but we didn't know that. That's not one that we know off the top of our head. So if you have a perfect square, when you break it up, you're going to have 2 perfect squares that multiply together, and then you'll get the answer. Okay? All right, 540. Well, looking at this number, I see 54, and 5 plus 4 is 9, so I know this is divisible by 9, right? I also know 54 is divisible by 9, so let's try 9, which is pretty simple. 54 goes into 9 6 times, so that means 9 times 60. And then this perfect square here is 9, and the square root of 9 is 3, so 3 comes out, and the square root of 60 stays in. And then we can start thinking of numbers that go into 60. So one number that goes into 60 is 3, so we can do 3 times 20, right? 20 is not a perfect square. Let's keep thinking. Does 4 go into 60? Yes, 4 does go into 60. So I'm going to say 3 and then square root of 4 times 15, right? And then the square root of 4 is 2. Pull out the 2, multiply it by 3 on the outside, and you get 6 square root of 15. And then look at 15. Factors that go into 15, 3 and 5, 15 and 1, none of those are perfect squares, so we're done. 6 square root of 15. Now some of you might not have started with 9. Some of you might have started with 4. Some of you might have started with 36. So the fast way, if you started with 36, was to just say, this is the same as the square root of 36 times 15. And what's the square root of 36? 6, and 15's left in jail. So there really there's more than one way to get the right answer. So as long as you got 6 square root of 15, you did it right. All right, so now method 2 is using prime factorization and look for a pair of factors. So now prime factorization is when you take a number and you break it down into all of its prime numbers that multiply together to give you that number. So if I'm taking the square root of 50, you could start by just making a tree, right? So you could start by just 2 things that multiply to give you 50, and they don't have to be perfect squares. So we could start with 2 times 25, we could start with 5 times 10, and so just to be different than the last time we did this problem, I'm going to start by doing 5 times 10. So 50 breaks into 5 times 10. And do I have a pair of numbers in there? I don't. So let's keep breaking it down. 5 can't be broken down anymore, but 10 can be broken up into 2 times 5. And so the prime numbers that make 50 are all three of these. And we're going to put all three of these numbers back inside the radical symbol. And I'm going to put them in order from least to greatest. So I'm going to have 2 times 5 times 5. And you should double check that 2 times 5 times 5 does give you 50. Otherwise, you've missed a number or you have an extra number. So 2 times 5 is 10, 10 times 5 is 50. So we did that right. So now what we're going to do is we're actually, to get out of jail, you have to be a pair. And the reason you have to be a pair is because think about this. You have a pair of 5s. What is 5 times 5? It's 25. What is the square root of 25? It's 5, right? So if you have a pair, that pair can come out as just the 5. So you pull out one of the pair. So I pull out the 5, and I'm left with inside a 2. Because technically, 5 times 5 is a perfect square. And you can pull it out as a 5. It's just that you're getting the root of it first. So you're pulling out one of the root, or one of the pair. All right, so the next one, 12, we could start this off 4 times 3. You can start it off as 6 times 2. Okay, you don't want to start off as 1 times 12 because 1 goes into everything. So 1 is not a prime or a composite number. We don't even worry about prime, or that number. So 12 is 4 times 3. You could do 6 times 2 if you wanted, and you'd get the same prime factorization. So now I don't have a pair, but I can break 4 into 2 times 2. So I have a pair of 2's, right? This whole thing are all the prime numbers that make 12. So inside my radical symbol, don't forget that negative sign. Inside my radical symbol, I'm going to have 2 times 2 times 3. And then you pull out 1 of the pair, right? Because 2 times 2 is 4, and the square root of 4 is just 2, right? So when you pull that out, just the 2 gets out of jail, and it becomes negative 2. And what you're left with are all of the things that aren't pairs, and 3 wasn't a pair, so negative 2 square root of 3. So if you notice, you're getting, these are the same problems we just did with the square roots method. It's just that we're using the pairs method instead, where you're like trying to find a pair of numbers. So both of these methods work. And I want you right now to pick the method that works best for you. So 480, a lot of people would look at that instead of thinking of a perfect square. They're going to say, well, that's 48 times 10. You don't have to do 48 times 10. You could do any two things that multiply to give you 480. I'm going to start with 48 times 10. So I'm going to break that up into 48 times 10. Well, neither one of those numbers are a pair, right? So now let's break up 48. You can break up 48 into anything, any two things that multiply to give you 48. So 48, I'm thinking of 8 times 6, me personally. So I'm going to do 8 times 6. And let's look at the 10. The 10, I'm going to break up into 5 times 2, right? And then let's go back to the 8. The 8 can get broken up into 2 times 4. And the 6 can get broken up into 3 times 2, right? Now I have lots of pairs here. I'm seeing lots of pairs. I also know 4 can get broken up into 2 times 2. So now everything at the end of my tree, this 2, this 2, this 2, this 3, this 2, and this 2, oh, and this 5 right here, all of the things at the very end of the tree are the things that make 480. So the tree method can sometimes get a little out of hand, right? Write down inside your radical symbol all of the factors that make up 480 in order. So I have 1, 2, 3, 4, 5 2's. 1, 2, 3, 4, 5 2's times, we've got a 3 and a 5. And then what I would do when you have trees this big, I would get out my calculator and I would actually multiply all of these numbers right here and make sure that they equal 480 before you start pulling out the pairs. But I'm just going to double check. 1, 2, 3, 4, 5, and then 3 and 5. So I have that. So now what we're going to do is we're going to circle pairs. Well, we have 2 sets of 2 that are pairs. So what you do is you pull out a 2 here, and you pull out this as a 2, and 2 times 2 is 4, but you have this negative sign out here, so it's negative 4. And then what's left on the inside are all the non-pairs. 2 times 3 times 5. 2 times 3 is 6. 6 times 5 is 30. So you get negative 4 square root of 30. Okay? All right, let's take 72. So now I'm going to show you 72 a little bit differently. We're not going to quite go all the way down to prime numbers because I just want you to see how this works. So suppose 72, instead of starting it off with 9 times 8, suppose I was like, you know what? I know 36 times 2 is 72. So suppose I started this by doing 36 times 2, and then I broke it up and did 6 times 6. All right, and so now I just noticed 6 times 6, I have a pair. So I could, and even though they're not prime numbers, you have a pair of 6s, right? So I could say 6 times 6 times 2, and 2 can't be broken up anymore at all. And so you have this pair of 6s. So that pair of 6s could come out as a 6, and then you have square root of 2. Right, so that's one way to do it. If you ended up doing the whole tree, you would end up with, here, let's do the whole tree right here. If I had 36 times 2, and I did 6 times 6, this would break up into 3 times 2 and another 3 times 2, and then you have this crazy tree that looks like this: 2 times 2 times 3 times 3 times 2. Whoops, I should throw this 2 here because it should go in order. And then if you look, you have a pair of 2s and a pair of 3s. You can pull out the 2, you can pull out the 3, and you would get 6. You'd still get that answer. But this way is a lot faster, right? So if you can find just any pair of numbers, you can pull out any pair, and then what's left that doesn't have a pair stays on the inside. All right, so the square root of 484 using the tree method. Again, I'm going to start this problem by breaking it into 4 times 121, but you don't have to start it that way. You could do it 2 times 242 or something like that. But I think 4 times 121 is easier. So now, maybe you didn't notice right away 4 and 121 were perfect squares, so you just start breaking it up. 4 breaks up into 2 times 2, and 121 breaks up into 11 times 11, and then you go and you put all those prime numbers in the box. You have 2 times 11 times 11, and then you have a pair of 2s that comes out, and then a pair of 11s that comes out. 2 times 11 equals 22. Okay, so you've got 2 pairs. All right, go ahead and try it with 540, see what you get. I'm going to start this one off with 54 times 10, me personally. You don't have to start it off this way, and if you did the problem already, let's just see if we get the same answer at the end. Okay, so 54 times 10 is what I'm going to do. And then I'm going to break 54 up into 9 times 6. I'm going to break 10 up into 2 times 5. And then break 9 up into 3 times 3. And those can't go anymore. And then 6 can get broken up into 3 times 2. Okay? And so now in my box, I'm going to put it in order. 2 times 2 times 3 times 3 times 3 times 5. And you really should, there's a lot of factors here, you really should double check and make sure that you got all of your factors. You can take your calculator, plug these into the calculator, and make sure it equals 540. If it doesn't, you missed a number or you put an extra number in there. So then your pairs, you have a pair of 2s, you have a pair of 3s, and so you pull out a 2 and a 3. 2 times 3 is 6. On the inside, you're left with 3 times 15, and 3 times 5, and 3 times 5 is 15. So you get 6 square root of 15. So we're finished with the notes. You can now try the problems down at the bottom using the perfect squares method or prime factorization, or you could practice both, like do one with the first method and then do the next one with the second method. Okay? And then look for a link to the explanations on how to do those problems, because I will also add a link for that as well. Good luck!